OpenAI DALL-E 2 and DALL-E 1 explained. Compare text-to-image generation models DALL-E 1 and DALL-E 2 and understand related models like VQ-VAE, Clip, and Glide. DALL-E 1 uses discrete variational autoencoder DVAE, next token prediction, and clip model for re-ranking, while DALL-E 2 uses clip embeddings directly and decodes images via diffusion similar to Glide. And I will go through several models so that you can get at least basic understanding of these two architectures. By the way, hello, I'm happy to see you. If I see you again as well, I'm not sure, maybe your first time. Then you can subscribe on my social media here, and for each post I create, for each video, I also have these posts where you can click on the links and get directly to the relevant things. You get these sort of summarization slides like posts, such that you can understand quickly, and then you can drill in for yourself or ask me a question. And yeah, I'm getting more deep into this. I'm studying machine learning. If you find any issues, let me know. I'd be happy to fix and discuss things. Okay, so let's continue. So we start with the clip model. Clip model is basically two models trained together, and we train them such that we encode image and text to the similar embeddings. This was trained on large data sets of images with captions from the internet, and it uses contrastive learning, maximizing causing similarity of the corresponding image and text. Image representations, what was interesting about them, that first time they contain sort of more semantics and style as well, and as well, it was possible to use them for zero-shot classification, but it was failing on more abstract or systematic tasks like counting. So again, how does this work? So this contrastive pre-training, we pass a batch of text, batch of images, they correspond together, and then we push cosine similarity to be close for the corresponding images and distant for those non-diagonal. Clip architecture, we have two separate transformer encoders. We have visual encoder, vision transformer, then we have text encoder, GPT-2 transformer, and those are fixed length embeddings that we can then compare. So these are sort of some two vectors that want to be close together if they correspond together. It was trained on 256 GPUs for 2 weeks. Kind of expensive, but yes. As well, I have posts on transformer, so you can read about in high level about all the interesting topics that I went into on the transformer as well. Here you can click through there. Okay, so now variational autoencoder. So I need this clip variational autoencoder and two more models to explain DALL-E 1, but it will be fast, I promise. So variational autoencoder models, so they model image distribution via lower bound or maximum likelihood. How they do this? We encode input image to a latent space, and then that we decode from that latent space back to the original image. We try to reconstruct it, and we require to have the specific normal Gaussian distribution on the latent space. By forcing this distribution, we are effectively modeling the distribution of the images. And how to implement this? We actually, once we are encoding, we are not encoding to one spot in the latent space. We are encoding into a Gaussian distribution with certain mean and variance. And then we sort of virtually sample from that using a parameterization trick, where we use this property of linearity of Gaussian. And thanks to the parameterization trick, we can then pass gradients through. And because otherwise random sampling is not differentiable. So what is loss function? So in the loss function, we first want to reconstruct the image as well as possible, for example, using LT loss and on the image pixels. And we want the latent distribution across all images to be approximately normal distribution. So once again, we encode images to distributions, and we decode them by sampling, and we want to reconstruct the image. And here the latent space is useful. We can even sample from this because it's a Gaussian, it has normal distribution, so we can travel across the distribution, and maybe you can even find some disentangled representations. I have also post on that. Okay, discrete variational autoencoder. So discrete variational autoencoder is a autoencoder where we map to discrete latent space. We use vector quantization. And that's the basic idea. It was presented in VQ-VAE 1 and VQ-VAE 2. Short name is DVAE. In the second version, we use image upscaling. How it works is that we encode image to latent space of 32 times 32 grid of embeddings. Then we quantize those embeddings. That means that we each embedding is assigned to the nearest neighbor that is present in the code book, in this constant, in this trainable array of code vectors. There are 8K of them. It's called Visual Code Book. Once we quantize these, we then map using a decoder to an image. So we use convolution neural network to 32 times 32, quantize to our vocabulary, and then decode using convolution network upscaling. Gradients are just copied over across the quantization. The loss function also tries to make the codebook useful, and at the same time there's a couple of tricks with top gradients, but this is the basic. We want to make the codebook useful. Okay, DALL-E 1. So DALL-E 1 uses both clip and discrete variational autoencoder. That's why we are talking about them. So DALL-E 1 is text-to-image generator. We provide text, it can generate image. It was introduced in paper. There's a link to the code. It generates images 256 times 256 from text, and it uses this discrete variation autoencoder that was introduced in VQ-VAE 2. The trick there is that once we can map to discrete visual codebook, we can generate this codebook using text models. And for generating using text models, we have transformers. So that's the trick here. We have text tokens, and then we can from text tokens generate visual tokens. So once more, DALL-E 1 training is that we train encoder. We start with just training encoder and decoder to this discrete variational encoder, and we generate those. So we learn this. What we focus there is to learn the decoder from the visual codebook as some kind of useful visual codebook. Then we concatenate text tokens with image tokens into each of them into a single array. And then we train to predict next image token from the preceding tokens using autoregressive transformer. Once we discard the image encoder, we can discard the image encoder, just keep the decoder and next token predictor. Then during the prediction, again we have a visualization tab here made of accordion. So this is a caption text here, and using the text we can then step by step next token can predict next tokens from the visual codebook. We get visual tokens. Using the visual tokens we can generate image. And that's how it operates. One more trick is that we use in DALL-E 1, we use clip model as a ranker. Clip model, as you remember, it can encode text embeddings and image embeddings to embeddings close together, and then we can use this then to rank what if the text and image really correspond together, to re-rank the results. This is a little bit expensive, but that's what was used in DALL-E 1. So DALL-E 1 uses this discrete variation autoencoder as mentioned. Instead of just copying gradients, it uses a more complicated trick, some kind of gradient, some kind of annealing. Basically, instead of just selecting the best fitting codebook word, it spreads to more code words, and then using some kind of soft some kind of Gumball softmax. And then it also uses code bit utilization. This method has some temperature parameter which then can be reduced to 0, and then it becomes very close to the original VQ-VAE, but I assume that it's useful for training. Okay, DALL-E 1 results. What was interesting in that, it was, I think, sort of competitive, or it has maybe a little bit better FID scores. What was super interesting about it is that it was highly preferred by humans. Just the images created by DALL-E 1 were very good. And so we can see the score here. Apparently, it was just preferred over 90% of the time. Compared to the DF-GAN. So the competing model was called DF-GAN. It was a generative adversarial network. And this was zero-shot setting. So I think zero-shot setting is probably, it haven't used this clip ranker, I think. Okay, DALL-E examples, so we can compare them. They are in rows, so the hours represent DALL-E 1. And if you have a look, I think in general, you could say that the DALL-E is usually better, but yes, this DF-GAN sometimes it looks pretty good as well, sometimes it's pretty bad. Yeah, so here DALL-E 1 is very good. Yeah, it was very good. So let's continue. To explain DALL-E 2, I need to explain diffusion models. So these diffusion models operate in such a way that they reverse noising, they de-noise images. And why is this useful? Because we can add noise to images very easily, and somehow this method then is working very well. Maybe exactly because how easy is it to create a large amount of samples. And so how it works that it can always, each step, remove some kind of noise. And so once you are creating the dataset, you take image and you add noise. So we go from right to left. And the generator then takes this complete noise and step by steps removes the noise. And by doing that, it generates image. Because here at the beginning, there's nothing saying what was in the image, but the model is sort of able to think of, hallucinate some kind of image from the noise. So okay, so let's go. So if you set a seed, of course, this will be somehow deterministic, but very unstable. There will be some kind of this butterfly effect in changes in this noised images. Okay, whatever. So let's continue. Train task is to, so the print task is to predict what noise was added and remove it. It uses mean squared error loss. And it's a little bit similar to normalizing flows like OpenAI's Glow. OpenAI Glow basically takes the image and maps it basically to a noise image reversibly. We can go there and back. And the representations there are as well useful. There are disentangled representations basically, and we can then, if we discover the directions, we can then modify the products. And I have also this video on disentangled representations. Okay, let's go. So OpenAI Glide. The OpenAI Glide is the diffusion model. It generates 256 images. I think it's the same as DALL-E 1. And it was introduced in this paper. It outperforms DALL-E 1 on human evaluation. So this one, Glide, was even better than DALL-E 1. It uses clip-guided diffusion. So this diffusion seems to work better than what we had there in DALL-E 1. So the task is to predict the noise, but given this caption. So we know what the image is supposed to be, so we will be hallucinating towards textual caption, because this is text to image. So, okay, so how do we do that? How do we know where we should go? Well, we use the clip embeddings. If you remember, clip is can take image, produce embedding, and so we can then navigate the noised image to go towards the embedding that we want, towards the text that we wanted. And but there is trick. The clip has to be also trained on noised images, otherwise the results are not as good. Okay, I don't know much about architecture in this one. I think some kind of transformer that's basically described here, and the text here in the Glide is embedded via another transformer, and the textual embeddings are added to the diffusion model in each some kind of attention layer as additional information. And additionally, in the loss function, we want to have additional term of a dot product with the clip text embedding, so we go in the text direction. Okay, DALL-E 2, introduced in this paper. You can have a look. It generates 1024 times 1024 images using text, using diffusion model. And it generates more diverse images and higher resolution than Glide. How do we do this? And I think it's even more efficient than a Glide. So how do we do this? How DALL-E 2 is trained? It generates clip model text embedding. So we have a text, we take the text, convert it to text embedding using clip. We spoke about the clip at the beginning. Then there is this prior network. The prior network takes the clip text embedding and converts it to image embedding, clip image embedding. And then we have this diffusion decoder that generates image from the image embedding. What's interesting about this one, that we can vary images while preserving style and semantics in the embedding. And also what was interesting, that they again tried something like this VQ-VAE, this quantization, but they found in the prior network, but they found that just the diffusion everywhere in the prior and the decoder as well just worked better. Okay, so how do we do the image generation? So we take the text, encode the text into textual embedding. This is clip. Okay, so this network is clip. We get the text embedding, and then we have this prior network. I think that's just diffusion. And we generate the image embedding. We pass the image embedding to the decoder, and the diffusion decoder generates the final image. And but yes, okay, so DALL-E prior network is this one that converts text embeddings to the image clip image embedding. It was tested They compared autoregressive with the diffusion prior, and the diffusion prior network was better and more efficient, so they used that one. DALL-E 2 decoder, it's very similar to the Glide decoder. It has a couple of tricks. So additionally, it conditions on clip image embedding by taking 4 extra tokens in additional to the text embeddings that were used in the original Glide model as well. Okay, DALL-E 2 evaluation results. DALL-E 2 is competitive in photorealism, but it can generate more diverse images than Glide. So you can select your text prompt and it will generate more diverse images, similar quality and higher resolution. And you can see it on this graph that we use this Glide guidance scale. I think that's some kind of a parameter that you pass to the model. They call the model here unclip. And if you sort of guide more towards the text, photorealism actually stops being as outperforming Glide, but in terms of image diversity, so how rich images, how various images can we generate, then in this case the DALL-E 2 is better in the diversity. Okay, so we can look at these examples. So these 2 last rows are from DALL-E 2. I can enlarge this. And if we have a look at the columns, I think these 2 last lines are mostly the best. But I must admit this make a sense model is pretty good as well. Yes, I must say this make a sense. Sometimes seems even nicer than the Glide, I would say. But the DALL-E 2 takes the cake. Okay, some additional nice images. These were, again, we have the text input as well. So the text input for these images is a teddy bear on a skateboard in Times Square, right? So we can input this text and it will generate these images. And I must say these images are just amazing. It's possible that they were somehow cherry-picked, but can you imagine that this was generated by a computer? This is very stunning. All right, so this is all from me. If you have any questions or would like to subscribe, you can go to my post. You can click on things you can study. Go through the summaries. You can subscribe on Twitter, LinkedIn. Do you use LinkedIn? Do you use Twitter? Or by mail for all new posts. Okay, so thank you very much and hope to see you next time. Bye bye.